In this video, I want to introduce you to something called conservative vector fields. But first, I want to talk about types of curves and regions that we are going to encounter. We can have simple and closed curves. If I suppose that I have a curve C described parametrically by r of t, where a is less than or equal to t, which is less than or equal to b, the curve C is a simple curve if r sub 1 of t sub 1 is not equal to r sub 2 t sub 2 for all t sub 1 and t sub 2, with a is less than or equal to t sub 1, which is less than or equal to t sub 2, which is less than or equal to b. That is, my curve C never intersects itself between its endpoints. The curve C is closed if r of a is equal to r of b. This says that the initial and terminal points of C have the same value. For much of our work, we generally assume that R in R2 or D in R3 is an open region. Open regions can be further classified by whether they are connected or simply connected. An open region R in R2 or D in R3 is connected if it is possible to connect any 2 points of the region by a continuous curve that lies entirely within the region R or D. An open region is simply connected if every closed curve in the region can be deformed or contracted down to a single point in R or in D. Visually, the types of curves for a closed simple curve looks like what a rubber band might look like just lying on the table that is intact. A not closed simple curve looks like a broken rubber band laying on the table. A closed not simple curve is a closed rubber band that's folded over itself. It might look like a figure 8, but it crosses itself somewhere in the middle. And a not closed, not simple curve is like an open rubber band that is laid down so that it crosses over itself. The types of regions could be a connected curve that is simply connected. This is a solid region bound by a simple closed curve. I could have connected, not simply connected. This is a region bound by a curve that might have a hole in the middle of it, where a closed curve within my region cannot be contracted down to a single point because of the gap in the middle of my region. I could have not connected, simply connected curves where I have 2 different distinct regions that aren't connected at all, or I could have not connected, not simply connected, where I have 2 separate regions, one of which is connected and not simply connected with a gap in it where a closed curve cannot be compressed down to a single point, and the other that is just a connected, simply connected region. So now I want to talk about conservative vector fields. A vector field f that can be expressed as a gradient of a potential function is called a conservative vector field. These conservative vector fields have some important special properties. A vector field f is said to be conservative on a region if there exists a scalar function phi such that f is equal to del phi on that region. Suppose that the components of f are given by the vector components f, g, h, and each of those components have continuous first partial derivatives on a region D in R3. Now, provided f is a conservative vector field, it means that there will be a potential function phi such that f is equal to del phi on my region D. This gives me components of f that are given by f is equal to the first partial derivative of phi with respect to x, g is equal to the first partial derivative of phi with respect to y, and h is given by the first partial derivative of phi with respect to z. If a function has continuous second partial derivatives, the order of differentiation in the second partial derivative doesn't matter. This means that phi sub xy is equal to phi sub yx. This implies that f sub y is equal to g sub x. Phi sub xz is equal to phi sub zx, which implies that f sub z is equal to h sub x, and phi sub yz is equal to phi sub zy. This implies that g sub z is equal to h sub y. This sets us up to formalize a test for conservative vector fields. The test for conservative vector fields assumes that my vector field F is given by vector components F, G, and H, and it's a vector field defined on a connected and simply connected region D of R3, where F, G, and H all have continuous first partial derivatives on D. Then my vector field F is a conservative vector field on D, which means that there will be a potential function phi such that F is equal to del phi if and only if the partial of F with respect to y is equal to the partial of G with respect to x, the partial of F with respect to Z is equal to the partial of H with respect to x, and the partial of G with respect to Z is equal to the partial of H with respect to y. For vector fields in R2 space, we have a single condition to satisfy, and that is that the partial of F with respect to y has to be equal to the partial of G with respect to x. So let's work some examples. I want to determine whether the vector fields are conservative on R2 if I'm given the vector field F is equal to the vector components negative y and x plus y, and if F is given by the vector with components 2x cubed plus xy squared and 2y cubed plus x squared y. In the first case, the vector with components negative y and x plus y, the partial of F with respect to y is equal to the partial of negative y with respect to y, and the partial of G with respect to x is equal to the partial of x plus y with respect to x. In the first case, I get negative 1, and in the second, I get positive 1. Since negative 1 is not equal to positive 1, my vector field is not conservative. In the second case, my vector with components 2x cubed plus xy squared and 2y cubed plus x squared y, my partial of F with respect to y is given by the partial of the quantity 2x cubed plus xy squared with respect to y, and the partial of G with respect to x is the partial of the quantity 2y cubed plus x squared y with respect to x. This gives me 2xy is equal to 2xy, and my vector field here is conservative. Now you get to try it. Pause the video and determine whether the vector field defined by F is equal to the vector with components xy is conservative on R2. When you are ready, restart the video to check your understanding. I need to find the partial of F with respect to y and the partial of G with respect to x. This means I'm looking for the partial of x with respect to y and the partial of y with respect to x. In both cases, I get 0. 0 is equal to 0, and my vector field here is conservative. This is how I test to determine if a vector field is conservative. Be sure and let me know if you have any questions.